$1,000 for a complete set of the world.
We haven't figured out what we're doing for lab tomorrow. We're having to negotiate with some of the other instructors to see whether we can use instruments and whether or not they can use them or not. But we'll try to give you an update. We have a test next Thursday, unfortunately. We will talk about it probably on this Thursday, when I get my stuff together and figure out what we're going to do and what's going to be on the test. I need to know that before I tell you. We are slowly but surely crawling our way through chapter 10, talking about polyprotic acids. And what else is there going on? I can't think of anything else. So we've been looking at systems where we have multiple forms of acids and bases, and figuring out, if you made a solution of this, what would its pH be, what would all the components be, and that kind of thing. And so we've shown you how to calculate all these things for the completely protonated form, the intermediate form, and the completely deprotonated form. And as one might expect, the pHs are pretty acidic for the acidic one, pretty basic for the basic one, and pretty neutral for the intermediate form. And that's pretty true for polyprotic systems, unless the pKa values are really close to each other. You see these kind of generalities across the board, and these are just concentrations. And you can see, I just summarized the 3 examples that we've done to date. So that's nothing new information-wise. And so we showed you, or at least we generated the equation for calculating the pH of the intermediate species, and it was a big, long one, and it sounded really fun, and it really is a lot of fun, but today we'll show you how to clean it up a little bit. If you always want to do the equation the long way, you're always welcome to. Every semester, there's always a question like this on the next test, and somebody wants to use the long drawn-out equation, and that's okay. You can always use the completely straight-up method if you want to. I'm not saying you can't do it. I'm trying to save you a little bit of time here when I give you these sort of little cheat codes, but you can do it the hard way if you want still. I don't have a problem with that. Anyway, the long story short is, here's the equation for the intermediate form of the acid. So this would be HL. And what are the pieces that we need for this value of H plus? And remember, we derived this last time. It was a lot of stuff, but we made it work. We need the Ka values, Ka1 and Ka2. Obviously, I'll give you those. I need to give you the formal concentration of the acid, F. We were looking at a 0.05 molar solution, but it wouldn't always be that. It could be different. What else would I give you? Oh, well, I wouldn't give you Kw, but Kw is always 10 to the minus 14th. I guess if there's anything, the few things that you have to know constant-wise, that would be a constant to know. You use it pretty much throughout here and other classes anyway. So this equation is a lot of fun. You say, okay, I can grind this out. Give me the equations. Let's make this happen. And you do it. And we figured out last time when we do this, I won't go through the gory math again. If we had 0.05 molar intermediate form of the leucine, we get a pH of 6.06. I guess that's on the board, so I guess why I'm writing it again, but I'm trying to belabor the point. So, but however, to try to simplify things in a matter of actually being able to take this test and not spend 20 minutes on one problem, there are some things we can do to clean this up a little bit. Whenever we see equations that have something that's added to something, we can look at that and say, are those two numbers of the same scale, or is one a lot bigger than the other one? So let's look at Ka1 times Ka2 times F versus Ka1 times Kw. If we can say that one of these is a lot bigger than the other one, then we can assume that it's going to be negligible. When I always say when it's negligible, it doesn't mean that it's not important. But if it's if it's less than 1%, then it is kind of negligible. You always, when I get change back, although it doesn't happen that much because I don't use much cash, you give the pennies back because I don't want to carry a bunch of pennies. It's the negligible part of the whole game. And so if you look at those two things, and then really kind of look at what those two things say, there's a Ka1 in both of those. So we can erase both of those, because they're going to be in both things. So we're really looking at Ka2 times F versus Kw. Because the other unit, of course, is constant to both. And so if you can look at those two things and say, what they're always doing in the hallway, that has to be sort of weird physics people. So Kw, of course, is 10 to the minus 14th. So you really just have to look at your number of the first part and see whether or not that is big relative to 10 to the minus 14th. Now, 10 to the minus 14th is a pretty low bar to clear. It doesn't take that much to be more than that. But remember, Ka2s can often be very low as well. So that being said, let's look at the previous example. The previous example, I said the Ka2 was 2.13 times 10 to the minus 12. This was in the previous example, 2.13 times 10 to the minus 12. F was 0.05. So that comes out to 8.75. Whoops. No, that wasn't right. That's not the right number. That's KB2, sorry. I have all pushing my notes here. So K2 is 1.8 times 10 to the minus 10. Okay, that makes more sense. Sorry about that. 1.8 times 10 to the minus 10th times 0.05 comes out to about 8.9 times 10 to the minus 12. Now, that's not a very big number. But again, you only have to be bigger than 10 to the minus 14th. And so you might say, well, that's almost 10 to the 11th if you round up. So 10 to the 11th versus 10 to the 14th is about 1,000-fold difference. So I could say for most of the time, unless Ka2 is really small, or if the formal concentration of the acid is really small, if this was really low, then that could be closer to that, and we couldn't make the approximation. But for purposes of tests and things like that I'm going to do, we can assume that Ka2F is greater than Kw. So that helps one side of the coin, which is really saying that we don't even care about this second term, because the majority of the number is coming from the first term. And then let's look at the bottom part of the equation, Ka1 versus F. This one's a little harder to make the assumption sometimes, but we do it oftentimes for the reason that we'll show you in a second. Sometimes those two numbers are pretty equivalent to each other and you can't make the assumption, but luckily that's not a big calculation and change. In this example, F is 0.05 and Ka is 4.7 times 10 to the minus third. So in this case, F is 5 times 10 to the minus second, Ka1 is 4.7 times 10 to the minus third. That one's not a great example of one where you can make the assumption, but sometimes we can. So sometimes we can find that F is greater than Ka1. And for purposes of the test, and I keep saying the test because we're going to have it here soon, is most of the time I will give you an acid that is appreciably stronger than Ka1, and when you can do that, then that part of the equation also clears out. So if we can rewrite this equation again to take into account what's really happening, the top term is now Ka1 times Ka2 times F over F. And you say, okay, I got an F here and I got an F here, we'll get rid of those. And H plus equals the square root of Ka1 times Ka2. Or if you like this on logarithm form, and you take the log of both sides of this, This becomes, or sorry, minus a log of both sides, just to clean it all up. This becomes pH equals 1/2 of pKa1 plus pKa2. And if you don't believe me, let's calculate what it was for the example that we've shown you, where if you do it out the long way, you get 6.04, or sorry, 6.06, sort of gave away there. If we do it for the previous example, we said pK1 was 2.328. This is for leucine. And pKa2 was 9.744. We got those off the big chart of the amino acids here. So that was 2.328 and 9.744. Of course, I'd give you those values. So let's say you do this. So it's really basically the average of the two pKa values. And if you do this calculation, which takes you, what, 15 seconds to do, you get a value of 6.04. So if you do it out the hard way, you get 6.06. If you do it the easy way, you get 6.04. I know which one I would choose, but I'm not you. This is a pretty established value approximation that holds for most polyprotic systems. Is the pH is simply the average of the two pKa values. Now again, it does, I'm sorry, go ahead.
What were the two things that you said would make it less significant?
Well, if you had a really low concentration of F, like if I did this at a 1 millimolar acid, or the Ka value 1 was really high, then you'd have to really grind out the hard way. But you can see that there's really not that much difference between the short way and the long way. You know, most pH meters don't even read very well down to the 0.01 digits anyway. That's kind of the last significant figure. So I would say, if I were you, but again, I'm not you, you could use this as your equation for the intermediate form of the polyprotic acid. Or you could use the other equation. Either way, you get the same number, plus or minus. But you can do it whichever way makes you the happiest. Some people like to do it the long and drawn out way because it makes more sense to them. And that's perfectly okay. All right, so to summarize, we can treat the completely protonated species as monoprotic acid, the completely deprotonated species as a weak base. So those are basically chapter 9 stuff. And then the intermediate form is the one that's the trickier part. And we can use either equation. We can use the equation with all the bells and whistles here, or we can have the short and sweet average of pKa values. I will accept either answer as correct for the test. And quite frankly, unless the Ka values are really different from are really close to each other, or F is really low, most people use the approximation and they get the they get the idea of where the pH of that solution is going to be. I will show you an example of how you can extend this a little bit further here in a sec to some other systems as well. You might also be wondering, I'm sure this is on the tip of your tongue, you're like, gosh, I wonder, can you make buffers out of diprotic acids? And the answer is yes, of course you can. Because any acid conjugate base pair can be used as a buffer system. And so the Henderson-Hasselbalch equation just kind of gets extended a little bit. So you can make buffers out of diprotic acids. I don't know that I'd use leucine as a buffer. That's kind of a weird buffer to make, I guess, out of an amino acid. That wouldn't be my first choice, but a diprotic system all the same. So you can make a buffers made from diprotic or even polyprotic acids. Any polyprotic acid could really be used as a buffer. Because what you're really seeing here is from the chart, the summary chart up here, is that most of the time you only have a little bit, you have enough of two of the species, and then the other species is a pretty low concentration. Like for example, the H2L plus, you have a little bit of this, a little bit of that, not much of L minus. The intermediate form tends to be not the best way to do acids because you kind of have continuing reactions, but you can make it work if you're in the right pH range. And then the completely deprotonated form, you don't have much H2L plus, but you can kind of form a buffer between these two species, whereas in the previous case, you can make a buffer between these two species. You can't really make a buffer of HL by itself because then you have an intermediate form and a base and an acid, and it really doesn't form a very good buffer because you kind of have competing reactions. But long story short is you can write the Henderson-Hasselbalch equation for basically two different regions. So remember, Henderson-Hasselbalch is pKa plus a log of the base over the acid, and so that's true here. You just have to make sure you're accounting for the right acid. So now we're including pK1, and this would be the concentration of the intermediate form over the acidic form. So remember that pKa has to correlate to the reaction that it includes. In the first Henderson-Hasselbalch equation, there's only one equation, so you don't have to worry about that. In the second Henderson-Hasselbalch equation, you now incorporate the second acid-base reaction. And now you include the ratio between the intermediate form and the completely deprotonated form. So there's two regions where you can have buffers. You could have it over here in the more acidic range, or you could have it down here in the more basic range. And both of those work just fine. So polyprotic systems actually make good buffers because they can be buffers in different ranges. So you have a little bit more applicability of the buffer itself. In a simple monoprotic system, you only have one spot where you can hit. And here you're looking at different spots, depending on your pKa values, of course. So let's make a buffer from a diprotic system real quick, and then we'll move on. Let's say you have 1 gram of KHP. You remember all friend KHP that we've been using in the lab as a primary standard for titrations. I bet you didn't know that this actually corresponds to what's called potassium hydrogen phthalate. Phthalic acid is actually a diprotic acid. You didn't really need to know that before now because it didn't really come into play. And if you include, we're going to add to that, we're going to add 1.20 grams of sodium phthalate. The KHP is actually the intermediate form of phthalic acid. So if you got rid of this this phosphorus, not phosphorus, potassium, why am I saying that? If you got rid of that and made that another hydrogen, H2P, that would be the completely protonated form of phthalic acid. Now, as it turns out, that pKa is actually pretty large, so it's happy to lose that first proton. And then if you mix it with a little bit of the completely deprotonated form, so you could think about this as that here's HP minus and P2 minus when we're just considering the acids and not worrying about the counterions that are in play. I don't know, it really doesn't matter that this is in 50 milliliters, it really doesn't matter. That's kind of an unnecessary thing. But what I do need to tell you that pKa2 is equal to 5.408. So the pKa, the first acid pKa is actually really low, so it comes off rather quickly. In fact, the second one is actually pretty low as well. So phthalic acid is not too, it's happy to give away those both protons, really. It's really not a very strong not holding on very tight. But let's plug all this into the Henderson-Hasselbalch equation that we just generated. So this would be pKa2 plus the log of, and this would be KHP would be the acid form, the intermediate form, but the acid all the same in this equation. And then this would be the base form, the Na2P. Just like in the previous equation, we're looking at the reaction between HP minus goes to P2 minus. It's sort of like the intermediate form again, although this one happens to be negative and 2 minus, but this all depends on the initial protonated state. So we have everything we can do to make this buffer work. We just have to plug everything in. So pH will be equal to 5.408 plus the log. I said there was 1.2 grams and 1 gram. And then all we need now is molecular weights, and I would give you those for a test just because I wouldn't make you try to figure those out. I don't know if anyone's ever done this in this lab or not, but what I used to often see when I was doing the grading for the labs is that people would think this is actually phosphorus, and so they'd put potassium, hydrogen, and phosphorus as their molecular weight, and things would be off by a factor of a lot, because this is really just an abbreviated form of phthalic acid. So 1.2 divided by 210.097, and this one is 204.223. If you do that, you get a buffer of about 5.47. So it's kind of around the same pH of the acetic acid buffer for the zinc lab. It's mildly acidic, it's not super acidic. But this shows you how you can make a diprotic acid into a buffer. Again, you could have made a buffer out of the phthalic acid and the KHP. It would just be using Ka1 now instead of Ka2. So it just shows you how you can extend it out a little bit further. It's really not changing the theory that much, it just changes kind of the players in the game. So as long as you're using the right players, you're using the species that you're given and the right Ka value, everything else is the same. All right, you're like, okay, monoprotic acids and bases, check. Diprotic acids, bases, check. Hey, how about triprotic acids? And you're like, oh boy, this is gonna suck. What about triprotic acids? And you're like, oh boy, how many more of these are we gonna do? This is the last one, thankfully, okay. And the good news is triprotic acids tend to work very much like diprotic acids, and so you can make a lot of the same assumptions. So let's say you have a triprotic acid, let's call it H3A. I'm trying not to go through this too fast because I just have these on slides. So you have a triprotic acid that can become H2A. Of course, that would be Ka1. This species can then, is an intermediate form. It can become H2HAA2. And that's the second system. And then HA2 minus can then lose this last proton. It become A3 minus, which is a Ka3 value. So what we really have here is 4 different forms of the acid. We can have it completely protonated, so H3, H2, H1, and no H, I guess. So you can have it in 1, 2, 3, 4 forms. Or if you like it, it can be in the base form, because of course A3 minus is not really a very good acid, it's a much better base. And so then it can extend out to, this could be KB1 or KB2 or KB3. And then remember the rules as we go along is that the KB values don't correlate directly to the Ka values. And in this case, Ka3 and KB1 correspond to each other. It just so happens that KB2 and Ka2, just because that's the way it works out, they happen to correspond to each other. And then KB3 is actually correlated to the Ka1. And so That's where a lot of people make mistakes on these ones, is they correlate the wrong one to the wrong value that was given. So some of you are thinking to yourself, oh boy, are we gonna have a whole nother equation that we're gonna have to learn for the intermediate forms of a triprotic system? Because now you think about it, we have an H2A here and an HA, and this one can act like an acid, this one can act like an acid, but then I also see how it can act like a base, and this one can act like a base. So now am I gonna have a 4-term equation that has another huge amounts? Well, the good news is that the equations that we came up with for the diprotic system work just fine for a triprotic system, again assuming that your Ka values are not on top of each other. So the good news is that we can again treat the completely protonated form as a monoprotic acid and the completely deprotonated form as a monobasic system. And the intermediate forms can use the same equations that we had before, but slightly different, because now we're incorporating, in the previous diprotic system, we had Ka1 and Ka2 here, and Ka1 and Ka1 as the second parts of the equations in the bottom part. And that still holds for the first intermediate form, once the first proton's been lost. But once you lose the second proton, then you start using the same equation, but instead of using 1 and 2, you now use 2 and 3. So now the second equation becomes an expression that uses Ka2 and Ka3 and K2 and K2 here. And this can go on and on. I mean, we're not going to do it for a quadratic system or anything like that, just because it's the same theories. But the other good news about this is we can make the same assumptions that we did in the previous system. Whereas in the previous system, we said that you can make a pH equals 1/2 of pKa1 plus pKa2. That still works, assuming that we can make the assumptions, which we hope we can. This equation right here is really functionally the same equation of the diprotic system, and so it can be boiled down, to use a bad term, into this little approximation. And this second term here, if you really look at it, it has the same functions, and so often can make the same assumptions, and we can make that equal to pKa2 plus pKa3. Because really we're canceling out the rest of this. We're canceling out the F's, we're canceling out the K2 and the K2 times KW terms. So these terms go away, the F's go away, and we're left with the square root of K2 times K3, which is this equation here. Again, if you love these equations because you're just like, I don't know what my life was going on before this, and now I know these equations and everything makes more sense, and you want to do it that way, then that's cool. But the rest of us will do it the short way and move on our merry way accordingly. But hopefully, you know, once you've seen the approximations, you can say, okay, well, I'm really looking at two different things here. I'm using 1 and 2 for this equation. I'm using 2 and 3 for this equation. I'm using KB1 here and KA1 here, and everything else hopefully makes sense. All right, so we'll do one of these really quick for a triprotic system. We're not going to go all the way through all the steps because it's kind of redundant. We've kind of done that a couple times now. So anyway, let's say we want to look at histidine, which I don't remember my amino acids very well. I've told you this 1,000 times now. But I guess it's the one that has an extra R group that has a ionizable proton. Okay. So histidine is triprotic amino acid. It has 3 different protons that can be lost. You have pK1, which is 1.6, pK2, which is 5.97, and then a third one, which is pK of 9.28. So you can see that you could have 4 different kinds of histidine. You can have H3, H2, 1H, or no protons. Doesn't mean there aren't any other protons, but no ionizable protons. And it doesn't really matter to you or to me, what order they come off, but the carboxylic acid is always the first one to leave, and then the remaining ones come off as well. And so we could have solutions of all four of these. We could have the 3, the 2, the 1, and the 0, and let's just call the F values of 0.1 for those. So, how are we going to treat these systems in a way that we might actually get out of here in the foreseeable future? Well, we're going to treat the H3S as a monoprotic acid. We're going to treat the 0.1 molar HIS minus as a monoprotic base, and then we're going to use the pKa values for the second and the third ones in our approximations to just calculate the pHs. So the rest of it is going to be pretty straightforward, one hopes. Okay, so let's start with the monoprotic system. And all this is in your book too, so this isn't anything brand new. Let's start with the completely protonated system, which we're going to treat like a monoprotic acid. And so this is the only reaction that we care about. So X and F minus X. And hopefully we would make the assumption that F is greater than X, but if we didn't, we'd have to lead to the quadratic. But on a test, of course, I'd give you ones where you didn't have to worry about that. So 2.5 is 10 to the minus second. That's actually equal to, that's actually equal 10 to the raised to the minus 1.6. I should have shown you those actual values, but I was lazy and didn't put that in the slide. So this becomes x squared over f minus x, and 0.1 minus x times 2.5 times 10 to the minus second. Your x value becomes 3.9 times 10 to the minus second, and a pH of 1.41. But again, it's just a monoprotic system, so it's really nothing brand new. Sometimes it leads to the quadratic, sometimes it doesn't. Or on a test day, it would definitely make the assumption that f is greater than x. So this really becomes Ka1 times f equals x squared, and that's a simple calculation. What about the second one? So H2S, if you get that one, and you get the values of Ka1 and Ka2 times F plus Ka1 times Kw all over Ka1 plus F. I went ahead and calculated it all out here on the slide, just so you can see how the sausage is made, just in case you wanted to work it out that way. And if you do that, you would find that the pH is equal to 3.83 down here at the bottom. Or if you want to use the quick and dirty way of just 1/2 of pKa1 plus pKa2, that said we're 1.6 and 5.97, you get a value of 3.78. Now, I think in this case the assumptions are not super great. Like you can see here, just looking at it, eyeballing it, you can say, okay, well this is 2.5 times 10 to the minus second versus 0.1. So it's not a great assumption because these two values are pretty close to each other. So that's why the assumption is not great. But overall, even if the assumption is not great, you're only off the pH units by a little bit. So 3.8 versus 3.83 versus 3.78, it's pretty small differences between the two. So it's not a big difference either way. And so, again, I would hope you could make the assumption and make the easier one. You could do it this way, but, I'd rather do it the easier way. So, and then we have another form that's in play. So we could have the HIS. So this is now the neutral form. And everything else is exactly the same, except now instead of using Ka1s and Ka2s, we're using 2s and 3s. So we just plug different numbers in for the Ka values. We have 2 and 3, and 2 and 2 here. Now in this case, you can see that the approximations are going to be great because a lot of the things are in play. This value here, this term is You multiply these two out, this is 10 to the 20th, that's minus 20, so that's pretty low. We're not gonna get anywhere close to that. And definitely 0.1 is greater than 10 to the minus 6, so we can get rid of that term altogether. And then if you do it out the hard way, you get 7.62. If you do it out the short way, you get 7.62, so tomato, tomato, you can see how that one goes. So again, make yourself, save yourself some time and use the shorthand way. So we've gone from pH of about 1.4 to 3.8 to now 7.6. And we'd be remiss if we didn't show you the last one. This would be the completely deprotonated form, 0.1 molar HIS minus. So all the protons have been lost. We treat this as a mono base and write the equation for this. Remembering again that this is KB1, not any of the KAs. So this is the only tricky part. Well, the second tricky part, of course, is that you're generating X's hydroxide, which you need to convert back to H+. Sometimes people will do like like when we have a problem like this on the test, although I don't usually do a triprotic system because it's just too much work. But people will get the hard part right, the middle part they'll get right, the hardest part, but then they'll screw up a little bit where they report this as hydroxide instead of H+, and so you're like, wow, you did the hard parts, but you missed the easy part. That sometimes happens. So KB1 would be KW over KA3, and that turns out to be 1.9 times 10 to the minus fifth equals x squared over F minus x. We're going to assume this is a monoprotic system again. If you do this, remember you're generating hydroxide, and hydroxide comes out to 1.37 times 10 to the minus third. In this case, you can make the assumption that F is greater than X. I think you're going to be safe to do that, especially considering how small that is relative to 0.1. You know, it's at most, looks like about 1%, 1.5% of the total. And then, of course, we have to convert that to H+. You can do that in any way that you feel most comfortable with. Convert that to POH or convert that to H+, whatever you do. And you end up with a pH solution of about 11.1, which kind of makes sense. It should be basic if you have a basic solution. You have to have something greater than 7, and it has to be greater than what the previous one was, which was 7.6. So the two intermediate forms have kind of middling, if not very neutral pHs. The last one is pretty basic, and the first one was pretty acidic. So 1.4 to 3.8 to 7.6 to 11.4. And so you can kind of see how it spreads out. And again, if you can make the assumptions, this doesn't become a super long problem because you can really see how the different forms come into play. All right, so if I was a mean professor, I would extend this out to a 4 and a 5 and a 6 system, but really the same theory holds. I mean, it's always the same kind of theory. Now with systems that have like 4, 5, and 6 acids, it does get a little trickier because sometimes those Ka values are really close to each other, and it makes some of the assumptions a little bit harder to make. So that's a reason not to use too many of those here. One thing that we also like to do, we'll end with today, is just to get a feel for what's actually in solution. Sometimes, you know, if I'm thinking about a reaction that I want to do in the lab, or we're doing in our teaching labs, and I think about like a buffered system, I think about what's really in the solution. Is it all acid or no base? Is it a good mix of both? Kind of, where are we? And we sometimes depict this kind of in a pictorial way here. So if you kind of think about these boxes, there's sort of a box here that represents HA, and there's a box here that represents A minus. And really what you're saying is that if you're in this box, you're containing a little bit more of HA. The farther you go to the left, the more HA you'd have. And as you go to the right, the more A minus you would have. And if you're on this line right here, we would say we have equal quantities of both. It's sort of the demarcation line between the states, you know, the Kansas, Missouri border. I was thinking Florida. The Florida-Georgia border. That's the Florida-Georgia games this weekend. I went to that game a couple times when I was in Florida. It's crazy. It's just like they have tailgating out in these like industrial parks, and can't explain it all to you guys, but it's just craziness. And then there's a football game that happens later. But anyway, so here's the border line here. And what the demarcation lines here are, is what makes this line the value is the pKa value. So this is for whatever acid-base pair you're looking at. So this could be 4 or 5 or whatever it happens to be. And at the top is the pH. So if you know the pKa of the acid that you're interested in, where your pH is relative to pKa tells you basically how much of the different forms do you have. If you remember back to Henderson-Hasselbalch, when pH is equal to pKa, you have equal amounts of both. So if you happen to have a pH that's equal to pKa, you would have 50% HA and 50% A minus. As you go more acidic, you're going to have more of the acid form and less of the base form. So, you know, as you go like a tenfold away, so if this was 5 and now this was 4, you would have like 90% HA and 10% A minus. And the farther you go to the left, you get more and more HA, like 99% or 99.9%, and much less of the basic form. Some people kind of like these kind of visual methods of figuring out what the principal species is. I'm a little bit more fond of numbers, but we can kind of agree to disagree on those fronts. When you throw a polyprotic system into this mix, you can see that now you have a lot of different stuff that can be in play. And so when you have a triprotic system, just like we showed a second ago, depending where you are on the pH range, you can have a mix of a lot of different things. But really what you're looking at, what's the predominant form? What's the species that's the most concentration in your solution? And for a triprotic system, you could have it where the predominant form is the completely protonated form. You could have it as the mono-deprotonated form, the di-deprotonated form, or the completely deprotonated form. And what you'll also notice is that the size of the boxes are not the same, because there might be a range of pHs where there's a long stretch where one species is predominant, sort of like going on a long road trip where there's really nothing to see for long periods of time, and hopefully you don't run out of gas. So you can see here, and these all depend on the pKa values. You can see here, the line here is pKa1, this line is pKa2, and this line is pKa3, and it depends on what those numbers are. So if this one is 1, 1, 5, and 10, then there's a big difference between, bigger differences here between 2 and 3 than 1 and 2. And then you can also see where your lines are. You can have basically a 50-50 blend of the completely the H3 form and the H2 form. At this line, you have an equal blend of H2A and HA. And then way, way, way over here, when the pH is very basic, whoops, back, you can have a blend of HA2 and A3 minus. Some people like these kind of forms because they help you kind of visualize relative to the pKa values where your, how much of each of those you have. In fact, I've actually seen people write these out for different forms and say, okay, well, if I have a buffer that's this pH, I have predominantly this and a little bit of the other ones. Which is great, except that most of the time, as scientists, we kind of want them in numbers. So we want to know roughly percentage-wise, actually number-wise, what we have of these. And so we led to what are called the fractional compositions. And instead of using a pictorial way of depicting what's going on in the reaction or solution, we can actually just physically calculate how much is of different forms. So let's start with, let's go back. So these are really equations that give the fractions of each acid and base at a given pH. And it'll be a fraction, so it'll be like 90% or 10% or 20%. We've already shown you how to calculate the actual amounts using the equations, but if we want to find out what the fractions are, like, you know, is it 40% or 10% or whatever like that, we can use these equations. So let's start with a monoprotic system. That's about as far as we'll get today. So a monoprotic system, HA goes to H plus and A minus, with Ka is our term that relates this. And we remember that the acid that we were given, this is the mass balance equation, that the acid that we start with has to be a sum of the acid and its conjugate base in whatever form they are. So if we started at 0.1 molar, we know that the sum of those two numbers have to equal 0.1. And then if we write out Ka, as shown, really, if you think about it, it's kind of a systematic equilibrium problem because we have two equations and we have two unknowns. And everything else is constant. If the F value is given, the Ka value is given. So we're going to be finding out everything else.